Good morning. I hope you're enjoying your Wilderness Labs DevCamp experience. Welcome to my session. My name is Bryn Lewis. I'm talking about using low-power wireless technologies with Meadow devices. I'm a Kiwi. You may have guessed from my Twitter handle or my accent. For a small nation, we seem to pop up in an awful lot of places. I'm a Microsoft MVP, specializing in Windows development, mainly the embedded kind. Azure IoT, mainly data acquisition and education projects. That's the stuff I actually enjoy. If you can hear a dog barking in the background, it's my neighbours. Our COVID-19 lockdown finished a couple of days ago, and she's missing her humans who've gone back to work. Some background about me. I started working in the industry in the late 80s, building software for pathology labs. It's the ultimate safety critical system. It wasn't uncommon for results to come out of blood gas analyzers and then be handed to surgeons or to ER specialists to adjust treatment plans. Then in the mid-90s, I worked on SCADA and telemetry systems for power stations, power distribution, mainly switch yards, and heavy industry. These days, what would be called the Internet of Things. These projects often had radio links, and I got interested in that technology. Well, to be honest, it was mainly often the radio links really didn't work as expected, and I learned a lot about them, debugging them. I then ended up working for a company who specialized in building trunked mobile radio systems based on a European standard, MPT 1327-1343. In a sort of odd way, this led to a job at Microsoft. I built a system for mobility management. It used a cluster of x86 boxes running Windows NT and Microsoft Transaction Server, MTS, and it was all back-ended, I'm about to show my age, by a DEC Alpha, 64-bit DEC Alpha running NT and SQL Server. I showed them the system, and then a couple of months later got made redundant, and when I was chatting to them, they said, "Oh, come and have a chat." And I ended up working for Microsoft Consulting Services for a couple of years. Since then, I've had all sorts of weird contract gigs, including working on tooling used by banks for AML and CFT, anti-money laundering and counter the financing of terrorism. It became really important after New Zealand signed the UN Convention on it. I have a sideline in doing software for configuring the propulsion systems of large water jet powered catamarans. These are used between the mainland of Australia and Tasmania, or the US Marines have some. They're huge. They can transport trucks and cars and tanks and so forth. They have a CAN bus network on board and joysticks in the bridge and out on the wings. These water jet motors are huge. The jet nozzles are a metre tall and they're powered by 1500 horsepower diesel motors. After 30 years, I'm really back where I started. I'm building IoT applications and some fintech software to pay the bills, and it now runs mainly on Azure. I have a number of Hackster projects and I'm fairly active on GitHub. Always makes me smile. The Microsoft Office suite automatically corrects Hackster to Huckster. I'm epileptic, so this presentation is recorded. The doctors are currently messing with my meds, and it would be bad if I checked out doing a live delivery. I'll be lurking in the chat and answering any of your questions, so feel free to type away. I tweet mainly about education and .NET topics, so consider following me. Thanks very much. Choosing a wireless communications technology is all about trade-offs. There's a lot of costs involved. There's the cost on the bill of materials, the cost of the individual components, the sockets and the plugs are even surprisingly expensive. There's the costs for the development of the hardware, the firmware, and the software. There's costs over the lifetime of the product for battery replacements, software updates, regular maintenance, things you wouldn't expect like solar panel cleaning. I was involved in a system which was built and deployed in a seaside town. It's amazing how much a seagull poo will damage a solar panel. It'll etch it to the point where it won't generate sufficient power to power your solution anymore. I also personally worry about the safe disposal of some battery chemistries which are chosen because of their long life, because of the toxic waste they produce in landfills. With product development, time to market is often important. DIY might have a cheaper bill of materials. It might be cheaper to use the IBM LMIC stack for Lorawan in an SX127X device. But if you get to market late, it might not matter at all. You need to think about the special requirements of low-power wireless devices. It's not like Wi-Fi. You've got much smaller bandwidth requirements. You're not streaming video. And you've got much less regular transmission, so there might be a wee bit more overhead in the establishment of a connection. You might only be sending a couple of dozen bytes 3 or 4 times a day. And what sort of range do you need? And in what sort of terrain is it? Do you need tens, hundreds, thousands, or tens of thousands of meters of range? Are you running your system inside buildings, or is it in an urban environment, or is it rural? All of these considerations impact the technology you choose. There are also network and national compliance considerations, especially if your product is sold globally. Getting a device certified can cost tens of thousands of dollars, and if you're deploying it globally, you'll need to get it certified for each locale. There are some globally agreed frequency allocations. The 2.5 GHz ISM, Industrial, Scientific and Medical band, is pretty well established in most countries. It can be a little bit crowded, but most of it works pretty well. But for other products using licensed or unlicensed spectrum, like LoRa, there are often different regional frequency allocations. In Europe, there's 433 and 868. In America, it's 433 and 915. There are special bands for Korea and for Australia and for South Africa. And having to get your system certified in those, if you've done a DIY, could prove quite expensive. You got to think about the whole lifetime cost. In my presentation, I'm going to focus on 4 technologies which I've used for building solutions. They're used mainly for personal, local, and wide area radio coverage. The first one is nRF24 from Nordic Semiconductor. There are varieties of chips. They come from individual chips the size of your pinky nail through to modules the size of a postage stamp, which contain power supply and antennas and so forth. There are even some nRF24 modules which are designed to be plugged into computers and have all the necessary logic for a USB implementation. The device is pretty limited, and it's used in cheaper consumer products. They cost about $1.33 per device for entry-level systems. The SX1231 from Semtech Corporation, it's often packaged by Hope RF as an RFM69 module. Comes in 2 different versions. There's a high power and a low power version. The high power version is a wee bit more expensive, and there are also different band versions. There's a 433 MHz version and an 868 900 MHz version. This device has quite a bit of onboard functionality. It's got crypto, addressing, retries, and so forth, and it's used in a few mid-priced consumer products. It costs from roughly $6 per device retail. The SX127X is often packaged as the RFM9X, again by Hope RF. Most people use it running in LoRa mode. It supports a couple of other different modes. So this device is used in business IoT applications because of its robustness in working in hostile RF environments and low power consumption. These devices cost from $12.69 per unit retail. The RN2903 from Microchip implements a full Lorawan stack with pre-configured regional band allocations and local and network specific implementation details, and it's got a certified hardware and firmware subsystem. They cost from roughly $12–13 per device retail. Beware, the terms LoRa and LoRaWAN are used interchangeably, even by vendors like Micro-E. They are not the same thing. LoRa is like a walkie-talkie you take skiing or tramping. It provides a simple peer-to-peer broadcast short message service. You send a bunch of text, everyone else can see it. There's no security, not necessarily even a CRC to check that what has arrived is correct. LoRaWAN is more like a cellular system with advanced security, device management, network managing, and global roaming capabilities. It just depends on what your application is and how you want to manage your devices. Just remember, LoRa and LoRaWAN are not the same thing. When someone's talking, always make sure to confirm which particular technology they're talking about. The first device I'm going to talk about is the nRF24 from Nordic Semiconductor. It comes in a bunch of different packagings, ranging from an IC about the size of your pinky nail through to a module with an SMA connector on one end. You just choose the device based upon your requirements for connectivity to external antennas and RF performance. The hardware is connected up using a serial peripheral interface, SPI, and two GPIO pins. One is an output pin, a chip enable used to control the power of the transmitter, turn it on and off to save power. And the other one is an inbound into the Meadow interrupt line. It's you can configure it to trigger when there's received signal, when the device has received a message for you, or when your message has been sent, and delivered successfully. It works in the 2.4 GHz ISM band and supports up to 255 channels. It supports 3 to 5 byte long addresses, which is great. You just got to make sure that your address length is consistent across your fleet of devices. There's also another downer, that you don't actually get the address of the device which sent you a message when you receive a packet. It also has pipes, and these pipes allow you to do sort of like multicast, like on the internet. You can receive messages with a wildcard final couple of characters. It supports 250 kilobit, 1 megabit, and 2 megabit transfer rates. It supports up to a 32 byte packets, not very long, particularly when you think about some of the overheads introduced by crypto and so forth. And it has automatic retries. You can say, hey, retry this message to ensure it gets delivered. And automatic acknowledgements. You can get the device to respond and confirm the receipt of your payload. It's used in quite a bit of consumer equipment. On the left is a CrazyFly Nanocopter. I learned how to fly quadcopters with one of these. They're great. Because they're quite light, it's about the size of the palm of your hand. Because they're quite light, they don't damage themselves when you crash them, and when you're learning, you crash the devices an awful lot. Also, the propellers are quite cheap as well. The Logitech dongle is one of the versions of the NRF device which has an integrated microcontroller and USB board. The device on the top right is a part of a presence commercial building utilization system. It's a presence detector. They put them up in offices. It's got an nRF24 module, and it transmits back to a controller sitting on the floor to work out how much of the office meeting rooms are being used. They also do devices which go under the edge of your desk to detect whether there's someone sitting at a desk. They use them for rent payments and also for working out when you arrive at work where you can find a free desk if it's a hot company which does hot desking. The device on the bottom right, you've most probably had a play with. It's a microbit. The University of Lancaster have built a radio module, and the radio module uses nRF24 connectivity. I'm in the process of reverse engineering that so I can connect microbits to the internet using my Windows 10 IoT Core Field Gateway devices. This was one of the cooler projects I worked on. I'm sorry about the crappy quality of the photo. On the left is a Netduino. On top of the Netduino is a Seed Studio Shield, and plugged into that is a WeChuck. On top of that is an embedded Coolness NRF24 shield. You could fly the Nanocopter with the WeChuck. The buttons on the front of the WeChuck were for hover and hold. You rotate the WeChuck forward and the Nanocopter went forward, and then you could rotate the Nanocopter on its axis using the joystick. I spent a lot of time flying that in my backyard. It was very cool. Reverse engineering the protocol was pretty painful. The device was originally, the Nanocopter is originally shipped with a dongle which you plug into a laptop, which isn't a terribly portable solution. This was great. You could just pick it up, put it in a shoebox and take your Nanocopter and fly it anywhere. If you want to give this a try, you're not really into soldering, you can buy yourself a FeatherClick Shield. I haven't actually tried this myself. My FeatherClick Shield is sitting somewhere between Serbia and New Zealand in a DHL distribution centre. Then depending on what sort of application you've got in mind, you can choose one of the different micro E-click devices. The one on the right is using a chip antenna. If you're building a device where you don't want any externally visible antennas and you want something with pretty reasonable performance, this would be a good way of simulating it. The device on the left is using a trace antenna on the circuit board. Some of these have been pretty patchy. The device on the bottom right has an external SMA socket so that you can connect up your own antenna, or a rubber duck or a dipole. They're great, but beware, if you drop it, it can break the circuit board or twist the pins. It's an expensive lesson to learn, and shipping times from Serbia to New Zealand aren't great. If you're not afraid of a bit of soldering, you can buy yourself an Adafruit ProtoShield and one of the low power or high power modules. You solder the low power or high power module to the ProtoShield and then run wires from the pins, from the 8 pins on the device to the relevant pins on the edge connector. This can be a pretty robust solution. I've got one of these sitting out in the garage transmitting data back to the house. If you're like me and you're waiting for your device to arrive, you can use jumper leads. It's pretty nasty, not terribly robust. Its range isn't too great either. Usually what you do when you build a circuit board is you put a more permanent solution, is you put a capacitor across the feed line and close to the device, and it improves the RF performance greatly. This one has only got a range of about 500 meters, even though it's using a high power unit which has got a range of about 1 kilometer. This was my test rig. I used it to ensure that the software was working as expected. I had to debug the SPI interface a wee bit because some of the methods weren't working quite as I expected. So let's go and take a look at the code. This is the sample application I provide for the NRF24 L01 library. The library was originally based on a port from Arduino by a GitHub user called Graylin. Another GitHub user called TechFu Ninja then did a Windows 10 IoT Core port, which this version is based upon. It provides a relatively simple interface to the NRF chip. There's 3 events, half a dozen properties, and everything's been set up with enumerations to make it easy to use. You'll see the different data transfer rates and so forth. You need to work out what your SPI port configuration is, then what pins you've wired your interrupt and your chip select and your chip enable to. Set the SPI bus speed. The mode is quite important, but just take it as read. Then just call send. The Windows 10 and NetMF versions had a synchronous send option. I've basically settled on doing everything with callbacks asynchronously. This device, I'll now download the software, is sending messages to a server located in another part of my house. You can see it doesn't take much code. Most of these are actually the default settings, and if you take away the code which displays the actual configuration, there wouldn't be much left. When you're first starting, make sure that you get the configuration on both ends the same. Just a slight pause as it starts up. There we go. There is its configuration, and it's successfully sent a message. Every 10 seconds it's going to send hello to the server located in another part of my house. In this second NRF24 based demo, I wanted to show one of the other benefits of the Wilderness Labs Meadow, the Meadow Foundation libraries. The Meadow Foundation libraries provide a series of drivers for a large number of common sensors and actuators and LCD screens. They're fairly fine-grained as well, which is great, so you don't have to include a huge library to drive a single sensor. Let's go and look at the code. You can see I've only had to include one additional NuGet. Then in the code, I declare the sensor, configure the sensor and attach it to the I2C bus. I then update it to force it to read the sensor, and then I can read and upload the data and send it to my Windows 10 IoT core. 3 or 4 lines of code to add basic IoT functionality to my Meadow application. The next device we're going to look at is the SX1231 from Semtech Corporation. It has a serial peripheral SPI interface with 2 GPIO pins. One is a reset pin, which is really useful. Returning the device to factory after you've messed up the configuration without having to power cycle it is really useful. The other line is an interrupt line used to indicate when a message has arrived or a message has just been successfully sent. It's often packaged as the RFM69 from Hope RF. There are 2 versions, a high power and a low power version. You've got to be careful with the high power version because it's quite easy to exceed the duty cycle limitations for the device. And I've cooked a couple of them in a test rig that I built to stress test one of my base stations. It's got a bit more functionality than a NRF24. It's got individual device addresses and broadcast addresses, which is really useful. There's a FIFO, only a single FIFO though, for transmit and receive payloads, and it implements AES 128 crypto. Well, it's a fairly basic electronic codebook, ECB approach. It doesn't use any data from the previous packet to see the next packet. This approach is fine for simple environments, but because the same raw text will generate the same ciphertext, this could cause problems if you're sending lots of the same data repeatedly. Where are these devices used in the real world? In Davis weather stations, for example. The device on the top right is a switch for controlling lights in a warehouse. It means you don't have to run cables down the pillars. You put these switches on and you can control different areas, the lighting in different areas of the warehouse. The individual addressing for these is great, so you can have like the switches you have in your house. Press one button, turns the light on, walk 5 or 6 pillars, press another button, turn the light off. I've also seen them used in the controllers for the high-ab cranes on the back of trucks for unloading concrete blocks and sheetrock and things like that. And my son is into off-roading, and I've seen the RFM69 based devices for controlling the winches on the front of off-roaders. I guess it's the addressing capability and maybe the crypto, which means they reduce the amount of code that developers have got to build in their specific applications. This is my RFM69 device. It's an Adafruit IO Feather. They come in 2 different versions, 433 and 900 megahertz version. You can solder a connector on for an antenna, but in this case I'm using a piece of wire, a DuPont lead. For a 433 megahertz system, you want a 16.5 centimeter long wire. For 868, 8.2 centimeters, and for 915 meg, 7.8 centimeters. That's a reasonably robust solution, and you can dismantle it. Note there's an offset. You need to put the Adafruit feather at the far left of the device. If you don't mind a bit of soldering, you can solder the wire in place, or you can solder the UFL connector on. I'm not necessarily a big fan of UFL connectors. They've only got a limited, say about 2 dozen cycle life. It's great for a product, but I found in schools and stuff, kids fiddle with stuff and they pop them on and off, and it's only a couple of weeks before the connectors fail. You can solder on a SMA connector. Those are pretty robust, but it does control the positioning of the device inside an enclosure, and you want to reduce the number of short RF cables and so forth. One problem with those is I did drop a device and it peeled the copper off the edge of the PCB. Make sure you use good quality connectors and are careful as you solder your wires on. Let's take a look at the code for interfacing to the SX1231. Initially I started with the SX1231 library, which had been ported from Arduino to .NET Micro Framework by a GitHub user called Roshimi. I tried for ages to get it to work on Windows 10 IoT Core, but couldn't get it to interrupt with any of my other Arduino devices. There seemed to be some odd settings. After struggling for a while, I stupidly decided to write my own, which is what the Meadow version is based on. I tried to set the device up with reasonable defaults. I looked at other people's libraries and tried to match their configurations where possible. You will need to tweak the settings to suit your application, your maximizing range, throughput, battery life, etc. The library is fairly simple. It has 2 events, receive and transmit, a couple of properties for setting some basic functionality, an initialize module method. You'll see the initialize method has an awful lot of configuration options. This started to get out of hand when I was trying to interrupt with other devices. I needed to be able to reach down and configure the SX1231 in a fairly detailed way to get it to work with some of the weather stations and so forth. Initially, I'd suggest just run with the default settings. Beware, if you set the encryption key values, it doesn't forget them. You actually have to explicitly set them back to nothing. It tripped me up a few times. Once you've got the device set up, you hook the receive and transmit events. I always dump the registers to see what's going on. Comment that out once you go to live, go to production. Then set the device, in this case, into receive mode. Every 5 seconds I transmit a short message, and then get notified of its transmission. If anyone sends a message to my device, either to the configured broadcast address or individual address, it'll be displayed as either hex or ASCII. This device also has CRCs on the payload so that you can check to see whether the message has been corrupted in transit. LoRa is a radio modulation technology for low power wireless networks. It was designed with low power consumption, short messages, and good in-building penetration in mind. It also has pretty good in-ground penetration, which is especially useful for Internet of Things applications like reading power and water meters, which are often located in basements or buried in footpaths. I've been able to communicate with a LoRa device buried a couple of inches under the ground, which is pretty impressive. Laurawan is built on top of LoRa and adds reliable messaging, network roaming, device provisioning, security, and a host of other useful features. Globally, most LoRa and LoRaWAN deployments use regional unlicensed radio spectrum, so you need to check with your local radio frequency service organization what the spectrum is and if there are any other additional rules around duty cycle, leakage into adjoining bands and so forth. The current distance record is roughly 830 kilometers. It took some pretty serious kit to do that. And there is even a Lorawan microsat in low Earth orbit. Lorawan client device implementations come in different classes. It's largely to do with the conservation of battery life. Class A devices wake up, send their messages, listen for a bit, and then go back to sleep. Hibernate, saving power. Class B devices wake up, send their messages, listen for a bit, then go back to sleep like a Class A device, but they also wake up every so often to see if there are any messages for them. Class B devices, which aren't really that common, usually have permanent power like a big battery or are connected to mains and are ready to receive and transmit continuously. With careful coding, more than 5-year battery life is possible. You just got to make sure that your device is hibernating all the time and you use the right sort of battery chemistry. Sometimes acknowledgement isn't required. Sometimes if you're sending messages quite regularly, it doesn't matter if the odd one doesn't get through, but you've got to be careful with retries. I worked on one project which ended badly when a base station was taken offline for maintenance. The devices in the field had a coding bug, which meant there was no limit on the number of retry attempts, and they also increased their transmit power trying to connect. It was winter, so there wasn't a lot of sunlight to charge the batteries, and it took a week before all the remote devices had charged their batteries sufficiently to come back online. There are other technologies like Sigfox which look comparable, but I haven't used them. You've got to be careful with the antennas you use. For testing, I often use a DuPont jumper lead trimmed to the right length as a temporary solution. Make sure you use the correct antenna for the frequency band you're transmitting on, as a bad choice can negatively impact your range. I find a 2.5 GHz stubby looks a lot like a 900 MHz one on my desk. Some people I work with mark antennas with a Sharpie as soon as they arrive to stop future problems. One of my friends, he puts a little blob of twink on his 900 MHz antenna, or twink, a whiteout, so they can't be confused. Make sure you use good quality connectors and antennas, as cheap and cheerful ones can reduce your range and your reliability. I had some cheap antennas and I found that they suffered badly from water ingress. So after a couple of months use out in the field, they started failing. For elevated outdoor antennas, a base station on the top of a building, consider a lightning arrestor, as an electrical storm could really spoil your day. One of my co-workers put up a system and then a couple of months later had to go and replace it, and the only thing left was the cable dangling off the bottom of the antenna. This is the SX127X. There are different versions for different frequency bands in use around the world. From Semtech Corporation. Has a fairly standard serial peripheral interface with 2 additional GPIO pins, one for resetting the device back to factory, which is really useful when you've made a hash of the configuration, and an interrupt line which can tell you when packets arrived, when there's received signal strength, when your packet's been transmitted, and a whole bunch of other more complex sequences for when you're using it as a Lorawan client. The devices, in my cases, usually run in a LoRa packet mode. There is also a continuous mode. It has no addressing, or very limited addressing capability, or crypto. There's just a preamble which wakes up the device, and an optional header feature, and you can get CRCs appended to the messages. There's FIFOs for inbound and outbound payloads as well. This is the Adafruit SX127, or they call it the RFM95 device. You can see I'm using a simple DuPont lead for an antenna. And note, it's got to be offset like the SX1231. The same rules apply for the antenna. 433 MHz, 16.5 centimeters long, 868 MHz, 8.2 centimeters long, 915 MHz, 7.8 centimeters long. The device is pretty robust. I've accidentally misconfigured it, I've accidentally plugged it in offset, and I haven't managed to kill it yet. It'll be great when the Wi-Fi capability of the Meadow is going, so I can use one of these to use a Meadow and one of these to as a simple field gateway device. Depending on how you want to set it up, you can do the low solder or no solder option. The no solder option is a DuPont wire. The low solder option is either soldering your own wire on a UFL connector or an SMA connector. Beware the number of duty cycles for the UFL connector, and the SMA connectors can be a little fragile. Make sure you use good quality connectors antennas. Cheap and cheerful kit can really reduce your range and reliability. We had issues with some antennas which when we suffered from water ingress when we used them outside, and it was only after a couple of months in the field that we figured out that our range was greatly reduced and we weren't able to contact some of our devices. I do lots of testing on my library. That's my stress rig on the top left. There are 8 devices pounding away at the base station, sending way faster than they should. I'm actually well out of compliance with local duty cycle regulations. I also test against different vendor stacks. The device on the top right is a Arduino based device, and I'm using the Arduino LoRa stack. The device on the bottom right uses a different vendor's chip. It's not a Hope RF chip. So I'm just making sure that I interrupt with different vendor systems. You'll see the device on the bottom right uses a quite cool self-adhesive patch antenna, and they're great if you've got a plastic enclosure for your device. You can just mount the board inside the box and then stick the antenna to the inside of the box, and it's ready to go. Let's take a look at some of the code. Initially, I started with an RFM9X library by a GitHub user called Emilsoft. Initially, it worked pretty well. I could get Windows 10 IoT Core devices to send messages, no problem. But as soon as I started trying to send messages to Arduinos or Netduinos, nothing happened. After trying to debug this and lots of frustration, I stupidly decided to write my own library. I spent a lot of time, and you can see it, bootstrapping myself up. I've got libraries for interfacing to different RPi shields, and I adapted these to suit the Meadow. There's only one shield currently for the Meadow, the Adafruit one. You can see I start by being able to talk to the shield. I then read a register, usually register 42, which is the silicon version register. I then read and write registers, figure out how to transmit data without an interrupt, receive data without an interrupt, receive with an interrupt, transmit with an interrupt, receive and transmit with an interrupt, and then finally have the huge number of defines and constants for configuring the device on the fly. After writing my own library, I figured out that the original library wasn't working because the algorithm used to calculate the 3 bytes for the frequency was wrong. I was transmitting on one frequency and no one could hear it. No non-Windows 10 IoT Core device could hear it. I set it up with mostly reasonable defaults. You might need to tweak them for your specific application to maximize range or throughput or battery life. You can configure the board rate. You can sort of start at a couple of hundred boards and work up all the way up to a couple of thousand board. You can control the headers on the messages. You can include CRCs. You can tell the library to ignore a message if it arrives without a CRC or an invalid CRC, things like that. I'll just start the library up. You can see that you set it up, you create the SPI, associate it with the pins, and then initialize it. You've got to make sure that the reset pin is wired up, otherwise the device can the pin can randomly float and reset, which can be really deceptive. There's not quite so many settings as the SX1231 device. I got rid of some of the more obscure ones. I wouldn't bring them in if anyone needs them. The maximum length of a message is 255 characters, which is more than adequate. You can also run the device in a packet mode, which is what I do, or in a continuous transmission mode. So let's start the code up. In this application, I initialize the device, turn on CRCs, go the Tim the Toolman Taylor and turn on PA Boost. You can see it's now downloading the code to the device, rebooting the device, and hopefully in a moment we should see it send some messages. There's a 10-second wait just to simulate what might happen in the real world and let everything stabilize. And then it goes into a loop transmitting a payload every 10 seconds. You can see I displayed register 42, Silicon version 12. They update this every so often. Quite a few of the libraries were actually wired to die if the Silicon version was wrong, and they bumped it just as I was starting this project, which was a bit painful. You can see now I've transmitted a 21-byte message and had an interrupt calling me back to confirm that the message was sent. If we left it running for long enough, we might even get a message from the weather station at the bottom of my garden. But because I'm in demo hell, it most probably won't. The RN2483 and RN2983 from Microchip are effectively globally standards compliant Lorawan in a box. They've got a pretty simple interface. It's a serial UART with 2 GPIO pins, clear to send CTS and RTS ready to send, and an ASCII command set. As I was initially programming them, trying to port some Arduino software, I was having flashbacks to the days of Hayes AT commands or 3GPP commands to dial calls and send SMSs, etc. There are different pieces of physical hardware to take into account the requirements for different bands around the world. You might have to make sure you buy the correct band, EU, US, AS, Australian, etc. Make sure that you set up the device so you can field upgrade the software. For example, in New Zealand, there are some fairly specific configuration. Here in New Zealand, we run the Lorawan AS923 Asia Pacific channel plan, and all sensors join on a pair of specific frequencies, after which they are then moved to other frequencies for general communication. If you're interested in giving this a try yourself and aren't keen on some soldering, you can buy a FeatherClick Shield and then choose a device which suits your local frequency range. You'll see even MicroE have mislabeled their Lorawan devices as LoraClicks. It drives me crazy. You'll see the one on the top right is great. It's got both 433 and 868 megahertz antenna connectors. Make sure that you've got the antenna connected to the right socket when you power it up, because it is possible to frag the device if there's no antenna connected to the one in use. I have a confession. I fragged my device. I can't do a demo. I was using a jumper lead. The 3.3 volt line peeled up, popped off the pin, swiped across the bottom of the board, and it killed the device. The replacement one is sitting in a DHL distribution center somewhere between here and Serbia. Part of me wishes I'd ordered it via Mouser. I would have paid a bit more, but it would be here by now. Lorawan is a hub and spoke network, so you need a base station. You can go for a developer class base station, like the one on the top right, based on a Raspberry Pi, or the one on the bottom right, which is a bit more robust. These devices usually run a version of OpenWRT and provide some basic configuration options. It could be quite complex coming up to speed with both this and the client side in one go, so I suggest you engage with either a local network provider or an organization like the Things Network, which has developer grade free capabilities around the world. You'll see here in New Zealand there are even 70 nodes. There's one not too far from where I live. There's also a few nodes off the coast of Africa where people have misconfigured their GPS and it's reporting 00. If you engage with a service provider, most of the processes are online. There's not a lot of support available. You're largely on your own because it's a couple of dollars a month per device, so there's not a lot of meat for support. There are also base stations available from companies like Ursa Wireless. Be careful though, DIY is a fairly intense exercise if you've not done it before. One thing you might want to consider is reducing the size of your message. A fairly common standards-based approach is the Cayenne Low Power Payload Protocol. It lets you include the data from multiple sensors in one message. It's standards-based, and it can give you significant savings in power and bandwidth. It supports quite a number of sensor types. For the Americans in the audience, it only does centigrade. Just a wee side note, there are only 3 countries in the world which use Fahrenheit: America, Myanmar, formerly known as Burma, and Liberia. The packet size savings can be quite significant. If you look at a temperature reading, 2 temperature readings fits in 8 bytes with 1 decimal point of precision, or you can get a latitude and longitude with 4 digits of precision and an altitude value in 11 bytes. Lorawan is a robust, well understood technology. You've just got to ensure that you don't try and build it yourself. I've encountered people who've said, oh, we'll use the IBM LMC stack on our Arduino. First thing they had is it doesn't work. Then once they've got it to work, it costs 10 grand or so to get it certified. Just buy an off-the-shelf chip and you're away laughing. Current state. So what have we got? Got a robust NRF24 library, which I've done some fixes to. We've got a robust LoRa library, which I wrote and will apply fixes to. I've got a proof of concept RFM69 library. It's not really ready for the big time. I've got a threading issue somewhere down in the heart of it. If at just the wrong time it receives a message as it's transmitting one, the message will get corrupted. I thought I had it fixed, but I added some more nodes to my stress test rig and it's still broken. I have DemoWare, Azure IoT, and Adafruit IoT field gateways. I also have a bunch of other gateways that are sort of a bit of a background task, which use MQTT for Bosch IoT, Lucent, us sensors, Adafruit using MQTT, and my device is Cayenne. You can see these are some graphs out of my Adafruit.io and my Azure IoT Central one. I use Adafruit.io for a lot of educational apps. It's $10 a month US, and you can have unlimited, up to a point, sensors, and stores the data for 3 months, I think, 3 or 6 months. You can buy more capacity and more throughput. On the right is Azure IoT Central dashboard. That's one for a weather station running, a LoRa-capable weather station running at the bottom of my yard. Works pretty well. Microsoft are growing its functionality. You can export the data out in Avro format. There are APIs for automatically provisioning the devices and so forth. Currently, my device I use a Windows 10 IoT Core Field Gateway to communicate with the SAS IoT package. I'm looking at updating this maybe to run under Unix, just a bit of an ongoing project. These packages are really useful. It's much easier to use an off-the-shelf package than write or debug your own. What would be useful? I've got a bunch of projects in the pipeline. For example, being able to check whether a message had been tampered with and ensuring it had been kept private with digital signatures and encryption on LoRaLink. Would that be useful? Would it be useful to extend the existing library to offer confirmed delivery with retries? Would it be useful to have other wireless chipsets supported, for example BLE or Sigfox? Would it be useful to port some of my existing field gateways to the Meadow? Once the Meadow's Wi-Fi is working, It'd be great to be able to plug a Meadow device in, attach it to the Wi-Fi and use it as a gateway for lots and lots of smaller and cheaper Arduino or STM32 based devices. Would it be useful to have more demo Meadow applications showing how some of the more advanced configuration options work? Would it be useful to have some demo end-to-end applications which show how to integrate all the way from the device back into, say, Azure IoT Hub, doing some ML and some time series analysis of the data? One of the projects that I've been looking at is a diagnostic tool for sniffing on-air messaging to see what's going on inside the packet. Initially start with a simple ASCII packet sniffer and then maybe add decryption or sniffing of LPP packets or something like that. As an advanced option, would anyone be interested in building in some IP6 low power functionality, like the doing a port of the OpenThread.net library? The global economy is in a bit of a mess at present. I'm a contractor. I might end up unemployed for a while, so I might have some time on my hands. If there's something that really appeals to you, drop me an email and I'll... Hope you found my presentation interesting and you're having a good Wilderness Labs DevCamp. If you've got any questions, I'll be hanging around in the chat for the next 5 to 10 minutes, or contact me. I'm at KiwiBrin on most common social media platforms. Thanks for your time and have a good rest of the show.